2012년도 상산 젊은 수학자상을 수상할 수 있는 칼트 김상현 교수님께서 컴플렉스 포 라이트 앵글 아킹그라는 제목으로 강연을 해주시겠습니다.
예, 감사합니다. 이런 문제를 통해서 Okay, so thank you very much for this opportunity to give a talk on my research, and this will be about a curve complex for writing a Darcy group. So I'll explain what it is and what's the use of it, and why do we call this as a curve complex for writing a Darcy group. So this will be a joint work with Thomas Cumberland at Yale. So the object of study for today is something called right-angle arcing group. So often it is abbreviated right-angle arcing group, or RAG. So this is a group presentation given by a finite graph. So suppose, let's say gamma is a finite graph, then one can consider a group presentation, so-called A gamma, or right-angled arcing group. This is right-angled arcing group on gamma. This is a group presentation where each vertex is a generator. Okay? And for each edge, we declare that they are commuting. So for each, we declare A and B are commuting for each edge AB. Actually, I caught a bad cold since last Sunday. Please allow me, forgive me if my voice cracks sometimes. So, and I'm also under the influence of some strong medication, so I might say something wrong. So, right-angled arcing group is a group presentation where the vertices are generators, and for each edge, there is a commuting relation. Okay? So this is a very simple presentation encoded by a graph. For example, if you have, say, right-angled arcing group on the complete graph, Kn, then this will be nothing more than there are n generators, and we declare they are all commuting because every pair of vertices are joined. Therefore, this is nothing more than Zn. Okay? Or even simpler example. If you have a right-angled arcing group on a discrete graph, then there are n generators, no relations, so free group. And actually, it can be a little more complicated if you have, say, a right-angled arcing group on half on 4 vertices. Then this will be, one can actually show if you know how to compute presentation for a link group. This is a link complement of link of 4 circles. And so on. So sometimes it remains for the group, sometimes it is not, sometimes it is. So extreme case, the two extreme cases are free abelian group and free group. So in some sense, right-angled arcing groups are interpolating between these two groups. So the theme, the subject that I'd like to address is subgroup structure of right-angled arcing groups. Subgroups. So the meta question is, what kind of groups can arise as a subgroup of right-angled arcing groups? And this theme, this direction of study proves to be very successful in the recent development in three-manifold theory. So let us recall some important facts about subgroups. So, well, the obvious, so some old result includes Servatius. Actually, there are two Servatius. I think there are a couple. So Servatius, drums, Servatius, 89. Is that, so if you have a right-angled arcing group, so for every n, at least 5, consider the n cycle. So pentagon or longer. Then this guy contains a surface group. And there is some ion SG embedded in Or you can say just there is an embedding. So there exists some closed hyperbolic surface group of genus G embedded writing darting group on a cycle. Okay? So this is one of the earliest examples of non-trivial so-called hyperbolic manifold group.
Will they say what is G in terms of M?
Yeah, sure, you can compute it. But this gets better. This gets better later. Yeah, you can, in this paper, STS, it's one of the earliest example of finding hyperbolic manifold in writing darting group, but they just concretely compute it. But this theorem got much better later. Actually, much later, it turns out the writing darting group on the pentagon contains all the closed hyperbolic orientable surfaces and some non-orientable ones. Well, yeah, non-orientable ones too. So yeah, so this is actually the next point, next idea. So CRISP GIST improve, or in some sense improve this to show that so for any closed surface with all the characteristics less than -1, the fundamental group embeds into some writing darting. So every closed hyperbolic surface group, except for this, so this when chi-s is -1, that is RP2, 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 and one can show that it is never embedded into any writing darting group, and as long as it is less than -1, you can embed it into some writing darting. And this got even better. So the big discovery last year is enables resolution of so-called virtual Hopkin conjecture. One of the most remarkable conjecture in three-manifold theory was resolved by proving just basically this. So if you have any closed hyperbolic three-manifold group, so pi on M embeds after taking up finite cover, embeds into some writing darting. Okay? And all those remarkable conjectures are resolved through this theorem. So the subgroup structure of writing darting also it is almost common to everyone. Whenever if you see this presentation for the first time in your life, it's such a simple presentation. This presentation where only relators are just commenting relations. What kind of subgroups what kind of interesting subgroups can you have? But it turns out that the subgroup structure is so rich that it contains remarkably various types of subgroups, even hyperbolic manifold groups. So, but I'd like to discuss about a slightly different, actually the opposite aspect of it. So these are, given an interesting group, you want to find some writing darting group contains it. My aspect is now given a writing darting group, it's more fundamental in some sense. Given a writing darting group, what kind of subgroups can arise as its subgroup? So one can consider. Let me go a little bit more this and talk about writing darting groups. Okay, so the main question today is, so given x and y, okay, so listing all the possible isomorphism types of writing darting given a writing darting group is just sometimes algorithmically impossible and algorithmically impossible. But we can be a little bit more this and try to answer given x and y graphs, finite graphs. Okay, when does there exist an embedding AX embeds into AY? So this seems a little bit much more modest, but it turns out it has not a simple answer, as you will soon see. Okay? So given two writing darting groups, the groups given by commuting relators, can you embed one to the other? Okay? So, there is a obvious, easy example of such an embedding when there is a subgraphs relation. So, easy fact is if you have induced subgraph X and Y. So induced subgraph means that so X is subgraph of Y, and all the edges of X came from Y. In other words, or more precisely, so edge of X is nothing more than all the possible pair which are joined in Y. So that is the induced subgraph. So if you have an induced subgraph, then there is an obvious embedding, Ax Y, such that the vertex can be considered as a vertex of Y. This way. But it's not all, unfortunately. Or fortunately, it's more fun. So one example, observation. So is that consider the Riemann-Darton group on a pentagon. Let's name the vertices as Q, A, B, C, D, and Riemann-Darton group on a triangular prism. Let's call the vertices A, B, C, D, E, F. Okay? Consider these two Riemann-Darton groups. Okay? So this pentagon cannot be realized as an induced subgraph of this triangular prism graph. Of course, it has a pentagon, but it's not induced subgraph. Right? There's a pole. But one can still consider a map from left to right, where Q goes to EF. So in this talk, this power notation means the conjugation. Then this is a group homomorphism because, well, so ABCD goes to ABCD. Now the only worry is the relator containing Q. So Q and A commute, and in the image, E to the F commute with A. Therefore, the relators are preserved. Same thing for D. Q and D commute. Now Q goes to E to the F. Now D. So E to the F commutes with D. So there is a homomorphism. From left to right. Phi is a homomorphism, but it turns out that Phi is injective. So one can use some combinatorial group theory to show that it is injective. So why did we care about this specific example? Well, so people were interested in actually this hyperbolic manifold subgroups of Riemann-Darton groups. And before this example, so people found Riemann-Darton group on a long cycle, or all this example from Chris to Twist dealt with gamma which contains long cycle. So the question is, when the graph does not contain a long induced cycle, long means at least 5. Long induced cycle, can it contain a hyperbolic manifold group? Turns out that the answer is yes. Because because we know that some hyperbolic surface group embeds into pentagon group, and this guy embeds into this triangular prism graph. Riemann-Darton group. So this contains hyperbolic surface group, although this is not really coming from the previous group. Okay. And there is another embedding discovered about the same time by the team of Crisp, Sagib, Sapir. So there is another embedding. This remark. Okay. So the answer to this question, when there is an embedding between two Riemann-Darton groups, is not as simple as it is. So that's why we considered, so Thomas Kudrada and I considered so-called extension graph. So extension graph is defined as follows. Suppose you have a finite graph, then one can consider gamma extension. This is a graph, huge infinite graph. How is it defined? This is defined as the vertex set is just nothing more than vertex conjugate, where V is the vertex of gamma, G is element of Riemann-Darton group. Therefore, it is a subset of Riemann-Darton group. Okay? So the vertices are conjugates of vertices as a group element of Riemann-Darton group, and you join two elements, say A to G and B to H, join if and only if they commute. Okay? Commuting is the most natural thing that one can do here. So for example, if you have a very simple graph, A, B, B. Let's say this is gamma. Okay? Let us consider gamma extension. Then you will have B, A. Not only A, you will see A to B, or A to B squared, or A to B inverse, and so forth. That will be gamma extension. A lot of elements. In other words, so in particular, gamma extension is even locally infinite in general. Of course, if gamma is a complete graph, then gamma extension is same as gamma. But in most of the other cases, gamma extension is locally infinite. So it is huge graph. Huge graph. So what's the use of it? The use is it gives some insights about the main question. So the theorem A is if you have so x, y are finite graph. If you have a x is induced subgraph of not only y, well, if induced subgraph of y is easy, there's an embedding, but if x is induced subgraph of y extension, then ax embeds into ay. There is some embedding from ax to ay. A little bit non-trivial embedding. Okay, so let's see an example. Consider, let's say y is this triangular prism graph again. So we call this called E, F, A, B, C, D. Okay? So this is y. Okay? Let us consider y extension. How does it look like? Well, so y extension contains not only these 6 vertices, but also vertex conjugates. There will be vertex corresponding to E to the F. And E to the F commutes with A, so you join. E to the F commutes with B, therefore you join, because E and F both commute with B. But E to the F, one can check by combinatorial group theory. E to the F will not commute with B or C. So this is like, well, and then a lot more vertices, like D to the B or A to the D. There are many, many other vertices, but at least these 7 vertices. And the edges shown here are all the edges between those 7 vertices. And there are a lot more vertices. And then you suddenly see pentagon here. So X is C5. Therefore, that observation, actually, so this is last year. So that observation just also can be considered as a corollary of this theorem. Therefore, by the theorem, writing darting group on pentagon embeds into writing darting group on this triangular prism group. Okay? So that observation is now corollary of this theorem. Now the obvious question then is, what about the converse? Okay? So this is sufficient condition to have an embedding from one writing darting group to the opposite direction, or to find an embedding. So, to remark. So this was first found by Casals, Ruiz, Andrew, Duncan, and Kazatskov this year. That there is a, so this appeared in Journal of Algebra. So there exists 2 finite graphs x and y, such that ax embeds into ay, but x can never be realized as induced subgraph of y extension. So the theorem is not if and only if, it's only sufficient condition. Okay? The converse is not true. There is an embedding, but X is not realized as induced graph. Okay? So what can you say about it? Well, so we need the notion of clique graph to describe the converse. So let's say X is possibly infinite. So it can be really any simplification graph. Oh, of course, so in this talk, at least I do not allow loop or multi-edges in graphs. So all the graphs are just simplification graphs, no combinatorial graphs. So possibly infinite simplification graph, and one can define clique graph. So K is a letter, not a number. It's just a way of making a new graph. A clique graph, vertices are, well, yeah, I should define what a clique is. So clique in a graph X, clique say K means, so it is a vertex that such that they are completely joined. So clique is some collection of vertices such that every pair are joined by an edge in the graph. So clique is complete subgraph, or vertex is a complete subgraph. Then vertex set of this clique graph is cliques in X. An edge. So you just collect all the cliques, not just vertices, but edges, triangles, K4s, K5s, and you join two cliques. If and only if union is also clique. Okay. So if you're interested in making class groups, so these kind of definitions will make sense later. So this clique graph, if X is a curved graph, this clique graph corresponds to a multi-curved graph on the surface. So we'll get to making class groups soon.
What's K there?
So K is a letter. Maybe it's not a good notation. Maybe I should say something like hat or something. But K is just a letter. Okay, so what is the theorem? Theorem is that if there is an embedding, so X and Y are the finite curves, then X may not be an extension graph, but clique graph of extension graphs, induced subgraph. X can be realized as an induced subgraph in this huge graph, locally infinite and clique graph. So using these two theorems, one can say many things about embeddings we can write in Darting groups. So this is not an immediate corollary, but maybe I should say corollary plus epsilon. So with some work, one can one can easily deduce these facts using these two theorems. So first of all, if Y is triangle free, then this is as good as it gets. So AX embeds into AY if and only if X is extension induced subgraph. So triangle, if the target is triangle free, this is as good as it gets. Also, this cycle writing Darting groups are somewhat mysterious, but one can answer the embeddings between them. So cycle, M cycle group embeds into N cycle group if and only if N-4 divides M-4. I don't want to talk about the zero denominator, so that is fine. But when N more N is 4, then this question is even easier. And what else? Writing Darting group on a forest embeds into a P4. P4 means path on 4 vertices. Okay? Forest is disjoint, finite disjoint union of finite trees, just by definition in this one. So we take writing the Artin group of forest, we can embed into a P4. So, well, if you're in three-manifold theory, this is just three-manifold statement. Because as I briefly shown at the beginning of this talk, this writing an Artin group on a tree is always a three-manifold group. So this is just saying that this guy writing some link corresponding to this forest covers the link corresponding to this people. And maybe lastly, AP4 is really unconcealable in the sense that writing the Artin group on P4 appears only when P4 is actually there. P4 is actually there. So the thing that I'd like to focus today for the remaining 15 minutes is the relation to mapping class group. How did you prove it? Okay. So okay, so let's see. So mapping class group, just to recall, is defined as follows. So S is a surface. So to simplify the argument, I'll just assume surface possibly with punctures. So it may be closed surface, but the boundaries are not contained. So you just remove closed disk and you keep you want. So possibly with open punctures. Then the mapping class group is defined as the homeomorphism. So orientation preserving homeomorphism group quotient by homeomorphisms isotopic to the identity. So you want to somehow discretize this mapping class group. So actually, it's the only mapping class I will use to state the results is so-called band twist. So if you have some part of surface that looks like a cylinder, and consider alpha is the core or co-core, and consider so there's some homeomorphism or class of homeomorphism called band twist. About alpha. Well, it is a homeomorphism, so everything will look the same, but the patterns will be different because it is non-trivial homeomorphism. So if you see some blue curve, and this blue curve will change after applying this band twist. This band twist is cutting alpha, cutting the surface along alpha, do 2-pi rotation, glue that. So it is a homeomorphism, but the pattern of the curves will change. So it will change like this. So there is actually it is more precise called a right band twist because when the curve meets the curve, it turns right. Like UK was turning right. So it is a band twist. So one of the recent discovery regarding band twist is as follows. So the theorem, so I and also Funar independently is that if you have, say, alpha 1, alpha k, so pairwise, non-isotopic, it's basically different, simple closed curves. Okay. Then there exists n such that So high powers of dentist. High powers of dentist is a writing document where X is a graph. Vertices are okay, and edges. You join two vertices if and only if they don't intersect. What is it? So you have a pairwise, non-isotopic, simple closed curve on surfaces. Then the claim is there is some power n, very large power, such that if you raise them to high powers, then high power dentist will generate right angle arcing group, where the graph corresponds to the vertices, and you join them if they are disjoint. Well, so to be more precise, this should be stated as disjointly realizable. That means you don't have, say, well, you can always make two curves intersect by this absurd way, but you can always remove that kind of intersection. So there is some representatives in the isotopic classes such that they do not intersect. So what's the meaning of this? Well, so recall, dentist is just cutting and going back. So if two curves are disjoint, those dentists will commute, right? It doesn't matter which dentist you apply first. It doesn't matter. So it is obvious that if they are not intersecting, they will be commuting. But the theorem, the meaning of the theorem is they will forget all the other relations. They will only remember commuting relations. Okay? So similar theorem was also found by Clay, Leininger, Langhans regarding so-called subsurface pseudoanisotopes. So some mapping classes, this disjoint support relations is just all that one will have to worry about. So let me so for the remaining time, let me give the key idea of the proof of theorem A. And this extension graph has lots of parallelism. So that is why I chose the title as that. So the parallelism between so-called curve complex and this extension graph. So finally, the last definition that I'd like to make is so-called curve complex. If S is a surface, there is a graph. I'll just call this as curve graph of S. It is a graph where vertices are so simple closed curves. So free isotopic classes of simple closed curves. Okay. And edge is the disjointness relation. Alpha class, beta class are joined if they can be disjointly realizable. So given a surface, okay, you record all the simple closed curves of isotopy and join them by an edge if they are disjoint. Okay? So it is a combinatorial way of encoding data of a surface. How do we encode the curves on a surface? So the theorem, this theorem, can be rewritten as follows. This theorem tells us that if X is induced subgraph of curve graph, right? This is exactly the same isotopic classes and disjointness corresponds to edge. So induced subgraph of curve graph, then AX embeds into mapping class group. This guy embeds into mapping class group. So this is the Koverda and also Fuller theorem. And more is similar to Clay Leininger models. So how we prove theorem A. So the starting point is start with any graph. So recall, so what is theorem A? Theorem A is if x is y extension, then ax embedded into ay. Okay? So for any y, there is a surface such that y embeds into curved graph as an induced subgraph. So this is just easy. Because y is a graph. Okay? For each vertex, you consider a circle. And when two vertices are not adjacent, you make sure those two curves intersect at one point. Okay? So you have just in R3, if you want, just a bunch of circles in R3. Consider the regular neighborhood of the circles near the surface that you want. So in other words, whatever graph you have, there will be this surface such that that graph can be realized as some induced subgraph in that surface. Okay? So vertex corresponds to single cross graph. So for each vertex, consider a circle. For each vertex, consider a circle. When they are not adjacent, make sure those two circles intersect. Define such a surface. So there will be this then. Well, actually, it can be better than just this. So for any sufficiently large n, it is only like more this. So in particular, there is this n such that ay embeds into the method class group P, sending V to the dentist hyperpower. Okay? So by the theorem. Also, these two. Writing another thing can be embedded into the class group. So, if V is a vertex, G is writing the Artin group, then where does V to G go? By saying phi. Well, it goes to phi G inverse P alpha V and phi G. But simple trick is conjugate of dentist is another dentist. Conjugate of dentist is another dentist. Because you're doing dentist in some other group. Conjugating is just you're changing it. You're considering symmetry of the surface. Therefore, so now consider, say, x y extension. Then vertex of x is first vertex of y extension. Recall this is subset of writing Artin group. In other words, vertex that can be written as, say, V1, G1, V2, G2, vertex conjugates. VK, GK. Okay? Then we have this diagram. Writing the Artin group goes to A1 for any n. One can consider of psi n, sending VI, GI to the group element VI, GI to the nth power. Okay? So this is well defined because if some VI, GI and VJ, GJ are joined by an edge, then means they will be commuting by definition of X. Well defined. And we have Pmap. Sending, so this will go to, what is it? T, Pg, inverse, alpha B, and X. Okay? And by the theorem again, so if n is sufficiently large, the same theorem again shows that is going to work. one because each vertex maps to power of band twist. Such a thing is injected by the theorem of Verda and theorem of Thuner. Therefore, by the elementary property of functions, the first one must be injected. And this is one of the proof. AX inversion 2. Okay? So basically this is it for the proof of the theorem. And for the remaining 1 minute, I'll just say there is a striking parallelism between curve complex and extension graph. Okay? So both are delta hyperbolic. So some hyperbolic manifold-like property of a graph. And if X is curved graph, AX embeds into mod S. If X is gamma is Y extension, AX embeds into AY. Or conversely, AX embeds into mod S and X appears in CSK. So except for this, which is shown by Verda and also Thuner, the rest are just our results. If AX embeds into AY, then X embeds into Y extension. And there are several other geometric similarities, but I think it's best to stop here. Thank you very much.
Questions? Comments?
You didn't explain what K is.
All right, so so K is a vector. Vector is not a number. So when I say xk, maybe I should say something like x ribbon or something. So K is from German and the complete vector.
Other questions? Comments? Okay, let me go on the questions. No, in Verda and Thuner theorem, can you reduce the number n? How you said the number
Yes.
n is
Yes, Thuner did that. So Verda paper, he gave n, just take n as sufficiently large. I think Thuner is almost as good as it gets. So he gave a quantitative version of the theorem. So which n you can choose. So his paper is more quantitative. But I myself couldn't read it before I speak.
So in mapping flexibility, the peanut is greater than 0.3, then actually no significant result, no output from mapping flexibility. So any hint or let's say the simplest profile.
Oh yes. So this is an interesting subject because this is for me this is the easiest way of generating unexpected subgroups of mapping class groups. So given a surface, so consider some subgraph of the curve complex, and writing the article on that curve, the graph embeds into this mapping class group, and then using this technology you can generate lots of subgroups of that writing article. So yeah. And actually, I was told by a four-manifold theorist used this approach to find interesting subgroups of mapping class groups. My answer is to find interesting subgroups of mapping class group, consider what kind of right-angle groups can arise in the mapping class group using these two theorems, and then find subgroups of this kind. Yes?
You mentioned that the connected sum of three copies of RP2 is not subgroup of the right angle group.
Yes.
Why not?
It needs a proof. So Chris List gave a detailed proof in his paper, but it needs a proof. So basically, every map from a surface group into writing darting group can be encoded as something called label reading map. Okay? So you can realize given homomorphism as some data on the surface. The data consists of several simple closed curves. Okay? Labeled simple closed curves like A, B, C, D curves. And for each fundamental group element, whenever you cross the curve, you read the label. A or A inverse and so forth. And this encoding can, so for any homomorphism, there is such an encoding. Okay? And then for RP2, 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 that encoding just doesn't work. It's related to non-orientability of the surface.
Okay, so let them speak again.